To everyone watching this video, thank you. I am Mr. Ish. I hope you are all having a great night. We're looking here at a completely optional video, optional topic, slope of a curved line. This is geared for those students in high school who will be taking calculus or who are taking calculus and they're starting that. The slope of a curved line, this concept comes very much in the beginning part of that calculus semester class or the year-long calculus class. When you're looking at slopes, you're all familiar with linear slopes because we all start by learning slopes of a straight line. But when we're looking at linear slopes, you're only really focusing on diagonal lines and you're focusing on horizontal lines. You never focus on a slope for a vertical line because vertical lines have no slope. The change in y divided by change in x for a vertical line, there is no change in x. You end up having a 0 in the denominator and you can't do slope determination for a vertical line. So as a high school student, your slope determinations are limited to these two forms, diagonal straight lines and horizontal straight lines. But for curved lines, it's a completely different matter. You can have so many different types of functions over there, all of which are curved, and you have to be able to determine the slope of a curved line. When you're looking at the linear line, diagonal and horizontal, and you're doing slope determination, you're looking at this formula, m is equal to y2 minus y1 divided by x2 minus x1. But all along, you're never thinking about it in this way, that you're always looking at some sort of average value here, average rate of change. ROC, rate of change, is a phrase synonymous with the word slope. When you're doing the slope determination for a straight line, it's always a rate of change, which is an average over your entire function. Why is that the case? Because if you were to look at some point here xy and some point here xy, it wouldn't matter where you would pick your points, your 2 points, because you need two coordinate pairs, y2 minus y1, x2 minus x1. The slope is the same no matter where you are on the curve. No matter what 2 points you pick, it's a straight line, the slope will always be the same, the rate of change will always be the same, but it'll always be an average rate of change because you've picked it over a distance of 2 points. For a curved line, you can't really rely on this average rate of change. You have to think about an instantaneous rate of change, because where you are on a curved line, the slope differs from one point to the next. That's the inherent fact of a curved line. Let's draw you a curved line. If you are looking at a curved line, you pick a point here and you were to look at the slope here, it would be very much different than a slope at another point on that same curve. How your curve is, the slope will vary based on that curve. Anyhow, you're thinking about instantaneous rate of change. The procedures you utilize to determine the slope of a curved line very much are based on these right here, but you have to do some sort of modification so that you can convert an average into an instantaneous. And what is that modification? We'll talk about that. And again, we're just doing a relatively straightforward preliminary introduction to this whole concept of curved lines. I don't need to show you how you determine the slope of a linear line. A straight line, you know how to do that. We're looking here at a curved line, and how does the process get started? The process starts very much you thinking as if you're looking at a straight line, but you modify it. And this is what I mean. You pick a point and let this point here be an x-axis value. You have a certain function f. You have to determine the coordinate pair here. If this x-axis value is an x, what is a y value? It would be exactly what your function would give you in terms of an output. You put an input, you get your output. The input is your x-axis value. Your output is your y-axis value, f of x. You think and you find another point which is h units away, and that right there represents an x-axis value, a new x-axis value. You find it on the curve, and now you have another set of coordinate pairs. You have an x plus h, which is your new x-axis value, and now as your output, your y value, you have f of x plus h. Because whatever you put in terms of your x plus h value, you'll get a new y value, and that will be your y2. This here is my x2, y2, this is my x1, y1. The procedure for doing a slope determination is to view and start with everything as if it were an average rate of change. You would draw a line, a secant line between these 2 points, and you would determine the slope of this straight line. You're looking at a curved line, but you're treating it as a slope of a straight line. And the slope of this straight line would be exactly what you're thinking, y2 minus y1 divided by x2 minus x1, and you would plug in these pairs. Your y2, x2, y1, x1, you'd plug these values in. You'd have f of x plus h, which is my y2. Then you do your y1, which is f of x. Then you do your x2, which is x plus h. Then you do your x1, which is x. and then you could simplify this because you have x plus h minus x, these x's cancel out. You would really end up having f of x plus h minus f of x divided by h. But this right here would be your slope. I'm using this for slope. The slope of this straight line. What is this straight line called? It's called a secant line. A secant line is a line which connects 2 points on a curve. It doesn't matter if that curve is however twisted or contorted. If you're connecting 2 points on that curve with a straight line, that's called a secant. But remember, we're looking right now with regards to a curved line as an average. We have to look at it as this. We started here, but we need to end up here. How do you end up from an average frame of perspective of thinking to an instantaneous perspective of thinking? You do it by modifying the secant line and by modifying this point. When you modify this point, you'll automatically modify your secant line. How do you modify this point? You eliminate this distance you are from your original point of reference. You shrink this distance, you make this point come closer and closer to your original point. As you do that shrinking, this secant line will very well change to a tangent line. And how you can imagine how it would change. Let me erase this for you and show you exactly what I'm talking about. You have all of these coordinates now written right over there. Look what happens when you have a curved line and you have one point. This is my point that I'm really interested in, and I'm looking at this point. I draw a secant line over here and I'm h units away over here. Now I shrink this distance and I draw another point. You see I've come a little closer to my original point. Now I draw a secant line over here and my secant line has changed. The slope of this line will be different than the slope of this line. Even though we're still looking at a straight line, the slope has changed because that straight line has been adapted to a curved line. Now I shrink this distance some more. I draw another point here and now I draw a new secant line. This original secant line, the second secant line, this third secant lines all have different slopes. But as you're seeing, this point is coming closer and closer to your original point. I'm going from an x plus h towards an x. I'm shrinking this distance. Now I'm going to draw another point here and I'm going to draw another point on my curve and I'll be able to draw another secant line. I have 4 secant lines. Each slope has changed. My goal is to bring this x plus h, shrink it all the way so that I end up on my original point. When I end my second point on my original point, I'll have the ability to draw a tangent line. That tangent line, if I'm able to determine the slope of that tangent line, the straight tangent line, I'll have developed the slope of that curve at that specific point, and it'll be your instantaneous rate of change or the slope of a tangent line. The instantaneous rate of change or the slope of your tangent line is what is your slope of your curved line. And you do that by decreasing this distance from your second point towards your original point. How do you annotate that decrease in distance in terms of a calculus terminology? You do that by means of a limit, and let me show you. And this is how you convert everything from an average frame of perspective into an instantaneous rate of change, and you do so by means of this specific limit, which I'm going to write for you here. Limit as h approaches 0, your entire equation for the slope of a curved line will become that. Why is this limit h approaching 0? What does it mean, or why does it make sense? It is exactly this. If your x here, your starting point, and your x plus h units here away from your original point, you have an f of x over here and you have an f of x plus h. You can think about it as h is approaching 0, you're not adding anything more to your original point. If here h was equal to 1, you're basically x plus 1. If h is equal to 0.5, now you're x plus 0.5. If h is equal to 0.001, you're x plus 0.001. If however h is equal to 0, now you're x plus 0, which is really x. You've landed on your original point. That's exactly what this limit means. You're not learning right now how you apply the limit. You're only learning right now how you start thinking about a slope of a curved line. The derivative of any function, which is annotated with this little prime, which means you're looking at the derivative, which means you're trying to determine the slope of a tangent line. You see how I'm using abbreviations? Slope of a tangent line is going to be determined as limit as h approaches 0, f of x plus h minus f of x divided by h. That formula right there, as you plug in your values, will give you your slope of your curved line, which will represent the instantaneous rate of change. Remember again, when I'm telling you, when you're looking at a slope of a curved line, you're trying to determine the slope at a specific point. When you're doing a slope of a straight line, you're looking more at an average. You're looking at the slope of the entire line because that slope does not change at all over the entire course of that line. You're always looking at a specific point slope on a curved line because wherever you are on that curve, the slope changes as the curve changes. Let's show you exactly how all of this plays out with a real life example utilizing this formula over here. I'm erasing it because I'm going to be writing it momentarily. You have a function, and we're going to end this video with this specific example. You have a function which is this: f of x is equal to x squared. You know it looks like a parabolic curve like this. You need to determine the slope of this function. Now the correct question is not you have to determine the slope of this function, because you need more than that. We're not talking about a straight line where the slope is the same no matter where you are on that line. For a curved line, you must have a specific point where you have to determine the slope. So the question would be this: for your function f of x is equal to x squared, find the slope at x-axis value of 2. And you know when you put 2 here in terms of your output, you have a y value here of a 4. So the question would be, find the slope of your function at 2, 4. And how would you go about doing it? You would go about doing it by first finding the derivative of this. The derivative of this is exactly utilizing this formula right here. Remember, there are many shortcuts when it comes to these functions, but you have to initially learn things via not the shortcut way, and your formula will be this: limit as h approaches 0, you have x plus h minus x all over h. Alright, and you can of course put the function over here because we're looking at your function. The function here will feed into exactly here. What's your function with an x plus h placed in it? This is exactly how it will be. You'll do x plus h whole square because your function is an x square. X plus h feeds in here, you get an x plus h whole square minus your original function is an x square all over h. You'd have to open this up algebraically. You'd have an x square plus 2xh plus h square minus x square all over h. You know this limit h approaches 0 will apply all the way to the end because you're still looking at a point over here, but you're still treating it as a secant line. You have to convert the secant line into the tangent line, but you don't have to physically do that. This limit is automatically doing it for you all along. What can cancel out over here? You can cancel this out, you can cancel this out. You end up having 2xh plus h square over h. You can isolate h over here, and you know you still have limit as h approaches 0. Isolate h. You have 2x plus h all over h. This can cancel out. You have 2x plus h with this limit as h approaches 0. As h approaches 0, h becomes 0 and it goes away. You're left with only just a 2x. What does this value give you at the end of this entire procedure? It gives you your derivative factor. What is the purpose of the derivative factor? It will very well accept this x-axis value into your derivative factor. You have a 2x. You have to find the slope of this function at 2, 4. You have an x-axis value of 2. You must put it over here. When you put 2 and you multiply it by that x-axis value, you get a value here of 4. What does that value 4 represent? It doesn't represent your y value. It just coincidentally looks the same as the y value on this function 2, 4. It's a coincidence that you're having the same value. But this 4 represents here the slope of your tangent line. And think about it. A slope of a 0 represents a flat line. A slope of a 1 represents a line which is equally steep, equally flat, relatively in the middle. A slope larger than 1 represents a relatively more steep line. A slope of a 4 will represent a quite of a steep line. We can now look at that value 4 and show it to you here on your function and represent what it would look like. It would look like this. Here's your function x squared. Here's your value here x 2, 0. You're looking up over here. A tangent line was drawn over here. This tangent line, which is a straight line, has a slope of a 4. It is 4 times as high as it is in terms of horizontal stretch. The change in y is 4 times that than the change in x. You'd go like this. You'd have a delta y over here, which would be 4 times that than the delta x. 1 this way, 4 that way, 1 this way, 4 that way. But the slope at this point right here, in terms of x-axis value, the slope of your tangent line would be equal to 4, and this right here is your slope value, which you are determining here from this question. So that's how you determine the slope of a curved line. You must have a function, you must have a point on where you are specifically trying to determine the slope, because the slope changes based on where you are on the curve, and you must be able to apply some sort of a limit formula where you are converting a secant line into a tangent line, and that formula will give you a derivative factor into which you will plug in your x-axis value. In some cases you'll plug in both x and y values, but normally you plug in your x-axis value. The answer from your derivative factor with regards to your x-axis value will give you your slope of your tangent line. Now with the slope of your tangent line, you know you have a 4, and you also know you have a specific point here on your curve 2, 4. You can take everything one step further and you can determine the equation of your tangent line. Let me erase this and show you that. The equation of your tangent line is no different than y equals mx plus b. Y equals mx plus b, and we now know our m is equal to 4 because we calculated. We have a specific point here which we know to be 2, 4. We have everything we could place right in here. We have 4 is equal to your 4 times 2 plus b. b is equal to 4 minus 8, which is a minus 4. The y-intercept very well finishes our equation of a tangent line, which would be y is equal to 4x minus 4. This equation here, the tangent line would very well represent this line right here. You can clearly tell that here it would have a y-intercept of 0, minus 4. But of course this graph here is not drawn to scale. It could be relatively flatter than it should be, but anyhow, you've seen everything here with regards to the depiction. You have a parabola, a specific point 2, 4. At that specific point, you have a slope on your curve equal to a 4. The tangent line has a slope equal to that 4 because the tangent grazes that function at that specific point. The slope of the tangent line very well mimics the slope of your curve at that particular point. The equation of your tangent line very well gives you additional information with regards to the steepness of that tangent line and where it interacts with regards to the Cartesian coordinate plane system. Anyhow, keep in mind everything that has been presented here. When you're looking at the slope of a curved line, you're not generally looking at a slope of a curved line, but you're looking at a slope determination at a particular point on that curved line, and that is an important distinction to be made with regards to the straight lines, where you're looking at a slope going similarly across that entire linear function. Average rate of change versus instantaneous rate of change, secant lines versus tangent lines, all of that represents clear differences between straight lines and curved lines. The limit formula here with regards to your derivative is the procedure which comes into play for you to determine the slope of a tangent line, which again mimics the slope of your curve at a particular point. From there you can very well determine the equation of your tangent line. All of this then should serve as a very good introduction for you all as you start learning this concept of slopes of a curved line. And again, it's at a particular point. Thank you for watching. Have a nice day.